let's look at Laplace transform of integrals. Okay, let's begin with a definition. A function f of t defined for t greater than 0 is called an exponential order function. This limit is satisfied. Limit as t approaches infinity of e to the power of minus st f of t equal to 0. So that is exponential order function. Now let's look at the Laplace transform of integrals using theorems. So let's look at the first theorem. If f of t is continuous and of exponential order and the Laplace transform of this function is capital F of S, then the Laplace transform of the integral 0 to t of f of u du is equal to 1 by s, the Laplace transform f of s for s greater than 0. Okay, let's prove this. So let phi of t is equal to the integral 0 to t of f of u du. Okay, now if we differentiate it, what do we get? Phi prime of t, we get f of t, and phi of 0 is equal to 0. Now let's take the Laplace transform of both the sides. So Laplace transform of phi of t is equal to Laplace transform of f of t. This can be written as, using our previous theorem which we learnt in our previous session, we get s times the Laplace transform of phi of t minus phi of 0. This is 0, so this goes off and we are left with this. Now let's rearrange this. Now the Laplace transform phi prime of t is equal to what? Phi prime of t is nothing but f of t. So which means we can write it as Laplace of f of t is equal to s times Laplace of phi of t. Now this can be written as s times Laplace of phi of t is the integral. So integral 0 to t of f of ut. Okay, and this Laplace of f of t can be written as capital F of s. Now let's bring this s to this side and just rearrange it to say that the Laplace transform of the integral 0 to t of f of u du is equal to 1 by s capital F of s, which is what we had to prove. Laplace transform of integral 0 to t of f of u du is equal to 1 by s fs. Okay, now let's look at one additional aspect. Let's take the Laplace inverse of both the sides, right? So Laplace of 0 to t of f of u du is equal to Laplace inverse of 1 by s f of s. These two cancel out. Yes. So we are left with the integral, and let's switch the sides. So Laplace inverse of 1 by s f of s is equal to integral 0 to t of f of u du. Right? So the same thing we can look at it in two different ways, in terms of Laplace and in terms of inverse Laplace. Okay, that is theorem 1. Let's look at theorem 2. Now what does the second theorem say? If the Laplace of f of t is taken to be capital F of S, then Laplace of f of t by t is equal to integral from s to infinity of f of s ds, right? By the Laplace transform, we know f of s is equal to the Laplace of f of t, which is equal to 0 to infinity of e to the power of minus st f of t dt. Now let's integrate both sides, this one and this one, with respect to s between s and infinity. So integral of f of s from s to infinity with respect to s is equal to integral s to infinity of this. So which itself is an integral 0 to infinity of e to the power of minus st f of t dt. Now we can change the order of integration because s and t both are independent of each other. So let's make this as 0 to infinity s to infinity e to the power of minus st f of t ds. I forgot to write. So this becomes des dt. Right? Okay. Now let's integrate 0 to infinity of, let's integrate this. So when we integrate, what do we get? E to the power of minus st by minus t f of t. Remember, we are integrating with respect to s from s to infinity dt. 0 to infinity of, so first we take infinity. This is minus e to the power of minus infinity, which means it goes to the bottom. Top 1 is there. 1 divided by anything infinite gives you 0. So 0 minus, now substitute s. We literally don't have to do anything. So e to the power of minus st by minus t. Right? This minus and minus gets cancelled and we are left with f of t dt. Now let's take, this is plus, so we can ignore this 0. So 0 to infinity of, let's put this t divided by t along with f of t dt by t. Now what is this? This is nothing but the Laplace transform. So Laplace transform of f of t by t. And remember, here we have s to infinity of f of s ds. Or in other words, we can say Laplace of f of t dt, f of t by t is equal to the integral s to infinity of f of s ds. Okay? So that is the second theorem. And let's look at it in terms of inverse Laplace. Let s to infinity of f of s ds is equal to phi of s. Right? Just to simplify the whole thing. So the Laplace transform of f of t by t is equal to phi of s. Now let's take the Laplace transform, inverse Laplace on both the sides. So Laplace inverse of Laplace of f of t by t is equal to Laplace inverse of phi of s. So Laplace inverse Laplace gets cancelled and we are left with f of t by t is equal to Laplace inverse of phi of s. Let's differentiate phi of s. Let's again rearrange this. Laplace inverse of phi of s is equal to f of t by s. phi prime of s is equal to minus f of s, which is equal to minus Laplace of f of t. F of t is equal to minus Laplace inverse of phi prime of s. Remember, how did we get this? We took the uh, Laplace inverse of this. So Laplace and inverse Laplace gets cancelled, and we are left with f of t. Since we are taking a Laplace inverse on this side, we have to take it on this side also. So Laplace inverse of uh, phi prime of s, and this minus from this side we are taking it to the other side, right? So f of t can be written as Laplace inverse of phi of s times t. From where did this suddenly come? Look at this. This t, if we bring it to this side, we get Laplace inverse of phi of s times t is equal to f of t. So I'm substituting that is equal to Laplace inverse of minus Laplace inverse of phi prime of s, and this t we can take it to this side, and finally write it as Laplace inverse of phi of s is equal to minus 1 by t times the Laplace inverse of phi prime of s. Yes. So how does this help? We are given a function whose inverse transformation is required. So here what we would be given is phi of s. We are given phi of s, and we have to find its inverse Laplace transform. So that is Laplace transform of integral. In the next session, we will look at some problem solving. That's it. Bye.